I usually try to include a material and then a modeling method. And this is going to be one of the cases where this is probably the biggest stretch, concrete and T-splines. T-splines is a modeling technique. And one of the reasons is that concrete is right now coming out of favor in use in construction because of the heavy footprint of CO2 gas that it emits during its production. So a lot of this presentation is going to be somewhat negative about the use of concrete, but we will spend a few case studies, should I say, um, looking at some beautiful examples of concrete construction. So I don't want to limit your vision on this, but contemporary talk about the use of concrete is undergoing a transformation right now. So before we get started, I always this is a structures course, and I'm always amazed at the failure of modern architectural projects sometimes, actually to humble us. The best laid plans of great engineers. In this case, this was in 2019, a year ago, a pedestrian bridge between a college, a university, and it was preformed next to the site to reduce the disruption of traffic. And then one day it was, would be hoisted into place, and then some additional structure would be added to it. And the story basically goes, and this is hyperlinked, so you can go to it. But there were noted some structural or some cracks in the concrete, and there were a host of errors that went along with this. One was the idea of prefabricating it and then putting it in place without the total structure that it was designed to have supporting it. Anyway, it was a great tragedy. It fell down before it was completed and killed 6 people. So, a reminder of the serious nature of the things we build. On a less intense note, warnings about the things we build or cautions to make us better designers, more aware. This is a mixed-use development going in on Elmwood Avenue in downtown Buffalo. And one day I run by this every day, and I noted that they started to apply this foam insulation on top of another moisture air barrier, and it really surprised me and made me start to think about what was going on here, especially because they were sealing the joints here between these. And I'm not going to make a definitive analysis of this, but I would point out some of the problems with the concept going on here. We have a barrier layer and a barrier layer on top of it. And then the possibility, which is what we've really learned in rain screen systems, that all systems have points of failure where moisture can get in. And because these two are touching each other, there's a great ability for capillary action to take over. And I'm sure the argument by the designers of the facade was that no moisture will get back there because this is sealed. And if it does, it can't get through the building because this is sealed. And I think that's the primary way that we see these failures in rain screen systems, or failures in wall systems, and why this constant reminder about the value of rain screen concepts in construction is so important. So if we look at a couple of other images of this installation, you'll notice that in further weatherproofing or barrier systems that were going up, you can see all the damage around that isn't being dealt with in any meaningful way. You can even see the tape being coming off. And there were attempts to cover areas that were exposed. But in other cases, a lot of the installation is going along with very little attention to this kind of detail. So I leave it to you, thinking about when you're designing your moisture barrier systems, your high performing walls, to think about not only what you're designing, but also how it will end up being installed and what potential problems could come from that. So let's take a few minutes really to talk about innovation in concrete, and this is really based on much of it on the reduction in the use of concrete. This is a hyperlink to a web page, and they'll talk about it being the second most material used on Earth, and it's the second largest CO2 emitter, accounting to 5 to 7% of annual emissions. So there's a heavy movement on, obviously, in architecture to reduce carbon footprint of our built forms because we use so much energy. And this article goes through, and I would invite you to read it, two ways that people are looking to mitigate, well, a couple of things. One is in the manufacture of concrete, how much CO gases has to be emitted, and a lot can be done with the idea of amending the concrete to make it lighter, adding structural elements to it like fibers, in some cases natural fibers, thinning down the structure, and using advanced printing techniques, 3D printing techniques, to create forms that are, by the nature of their form, inherently structural. So there's all kinds of research on that front. Even the idea of glass reinforced concrete, glass fiber reinforced concrete panel systems, still giving the idea of massive elements, but very lightweight panels being fabricated from that. And this is a video. It's worth watching because it touches on a couple of different dimensions about the advancements in the state of the art. This is a fabric woven shape that was erected, and then concrete was applied. So the actual fabric itself is part of the formwork of its creation. So here we have the mesh analysis of the form. It almost happened so fast. Let's go back to that. I'll just pause that for just a minute, if I can. So here we have this laid out for the knitting machine, and this is the order of the printing of the fabric sections to create that shape. So they unwrapped it and laid it out into a manufacturable component, something that we are learning how to do in our current course. I guess one of the unique things about this is the idea that this formwork is actually just rolled up. I believe there's an image of them transporting it across the country in suitcases. So the idea that it can be moved very easily. Obviously, there's a lot going on in these types of systems. So while we see the lightweight formwork of the fabric, we still have all of this kind of other structure to hold that frame up. Obviously, there's all kinds of analysis issues about whether we're actually saving materials. But once again, very unique about how much tension is put on it. I guess one of the questions would be, why do we need to make it a concrete item, except that it makes it completely self-standing and rigid. And there they are. They apply a couple of coats of different materials. And so that's I guess, the bleeding edge of technology in the formation of complex concrete structures. So we'll go back to I'll just stop this from playing. And there's a few other things here. Obviously, these are well worth watching. This is a floor system, and the idea here of removing, by using finite element analysis and regenerative design, to remove the concrete that's not needed in a floor deck in areas and where the structure is needed to provide the concrete, so that we have a lightweight, high-performing surface. And I think that concludes that amount of presentation. So keep it in mind that I guess the overall feeling in the industry today is really a discouragement over the use of concrete. And keeping that in mind, we still want to achieve beautiful architecture. So this is a kind of a compare and contrast about alternatives. So here we have Saarinen's TWA building. Beautiful thin shell concrete building. You could say it's really actually a very efficient use of concrete also. So I don't mean to make that a dig on this is a concrete structure. But here is the National Air and Space Museum, an entry canopy system. Obviously, almost a complete duplicate of the Saarinen TWA building. But I'm showing you this, just the idea of we can still create great forms and use different kinds of materiality. And obviously there's some downsides to that, the exposure of this framework. But it could be conceived that there is fabric supplied to both the exterior or cladding systems and the interior. And obviously, just moving towards engineering these things to being both high performing, beautiful, and reducing our carbon footprint in the way we choose to utilize materials. Calatrava's work is also, I think, really strongly influenced by Saarinen. And this was the idea of expressing concrete, these mass systems, and I couldn't help but see the similarities in looking at this project and then his work, and how even great architects take the lessons of other great architects. So I see so much here that, to me personally, I would have felt like I was lifting the actual work from another, and that may be clearly expressed and admitted. But nonetheless, it's to me, I took it as a lesson about what even great people use as inspirations for their ideas. And here's his work in the I guess the ground zero area of New York City, and a transit hub, major and beautiful structure created there. We can dig in just a little bit into the TWA. I think one of the reasons I wanted to spend just a few more minutes with this is the complexities of the shape and the humbling of how these were done prior to computers and advanced modeling techniques. This is a good shot because it also kind of communicates how thin that shell is of the building. So we have these built-up edges, but we can see that the overall thickness of these systems is really quite thin. And here it is under construction. This is back in the 50s, early 50s, I believe. Just a beautiful shot of this thin, lightweight shell system. This is an important image to think about because of the, you can see the massive amount of formwork and structure that's needed to create this type of a shape. Because you have to pour a liquid material and wait for it to harden, you have to have some way of structurally supporting that through that transition. Just a close-up shot of these shells coming down to their load-bearing points, and this natural, what appears to be natural and well thought out transition of these loads to foundation systems. You can still see the amount of rebar laying around for future work of reinforcing all of this concrete that's being constructed. So this has been recently restored, and so it's a really popular project. And it really has always looked pretty good as far as the appearances of it when I've been at that airport. But this is some look back at the some of the original construction of it. So you can see a lot of the you can see the wood formwork that created these shapes. Once again, I'm really quite impressed with the idea of the thin shell shapes here. Obviously, you can see how they're working to create drainage, and pushing up at the ends to create a more attractive form from grade level. And I think a lot of this work was done, and I don't have all of the, obviously I haven't done a significant amount of research on this project, but the idea of the shapes and forms really being generated in model type methods and then translated back to drawings. So here we have a whole, just a great shot of a model room at that time, and the experimentation of roof systems, the the construction of these very thin shells, the idea of looking at how you would transition your grid systems to it. This is actually a contemporary picture of the renovated facility. And this is a historical one, so it really retains a lot of its original integrity. What's also, to me, noteworthy is these bow trusses that are supporting the glazing systems. They look really very advanced for 50s design, and really create a very thin, lightweight kind of glazing system. And we'll look at glass in the future in this course, so I think it's really important to note how advanced this glazing system was for its time. And Hadid's work is kind of, I put this here to kind of say, how would we build it today? And instead of it being a mass of concrete with reinforcement in it, we're now starting to look at using grid systems, space frames, in order to create the underlying superstructure. And there's some inherent advantages to that. It is actually, we don't need to create scaffolding to support the structures because they self-support as we put them together like Tinker Toys. So there are all kinds, a host of efficiencies that are gathered on site during the construction of these complex shapes. There is on Blackboard a link to the construction of the Sydney Opera House, which is where we're going to go next. Another thin shell kind of, well, this is actually not a thin shell. It appears as a thin shell concrete structure. And obviously that's a great compare and contrast because as you'll see as we get into these shells are now very thick and massive. And here's a cutaway of the building, and actually they don't do anything to disguise this kind of idea of massing. This isn't really as thick as those sections are, but you'll see how much material is involved in that because they are constructed of these rib systems. Obviously, what's so neat about looking at the Sydney Opera House for me as someone who's involved in instructing computational design is how similar this looks to the things we're doing today as far as panelizing systems. The way the forms are all changing as they move along a surface, but they still are the same component basically. But in this case, this is a lot of structural concrete that went into this project. Possibly way over-engineered. I think there was a huge concern because there's very little familiarity with designing these forms. There's a story of having started the foundations and then having to remove them because once they had engineered the shells, the weight that was bearing on them exceeded what they were designed for, so they had to be reconstructed. So here we have an interior view of those ribs coming up. You can see how deep they are. And also, what a beautiful form this creates on the interior of the building. Still a massive use of concrete. So back in those days, they didn't have the advantage of computational algorithms and computers to do all of the calculations. If they did, they would do them manually, and that would become exhaustive and impossible as far as the amount of man hours required. In the video, you'll see some discussions about how they came up with these final forms, the simplicities of them in order to make them mass producible. I see this image and I think a lot about boat building. I'm sure that people brought the technologies that they knew with hull design. This is a concept called lofting, where you take the geometry and shape at a certain point and you pull it off, and you can generate through two-dimensional drawings three-dimensional curvilinear shape. And this is it now being transferred. In this case, the lofting happens out onto sheets of plywood where actual members are then literally fabricated from that. Another great reason to look at the video is just this discussion about how much testing went into it and the manual kind of verification of calculations. So here we're actually loading models of the shell with weights. Here's the bottom side of that, weights hanging down, in order to verify what calculations they did. And there is mention that computers were used, but they were in their infancy. So the kind of calculations and sophistication is much different than we have today. These were precast and then hoisted into place. So this gives you an idea of the human scale of them. So once again, we see that kind of diagonal bracing, not unlike what we think about and do in space frame construction. And this is a great image of the underlying structure and then the cladding system. And I think the cladding system really holds up today as far as its beauty and interest. This, I want to say chevron for lack of a better word, patterning. And then up close, the idea that these are covered with ceramic tile, the glazed contrasting with the unglazed tiles, creating this really delightful, beautiful, sophisticated look to the surface. So that completes the look at the Sydney Opera House. I guess one of the last things I wanted to really kind of discuss is some of the, I guess, the stretch of the absurdity, or I hate to use the term absurdity, but the stretch in where we're going, maybe a pun intended because we're looking at fabrics, of what our advanced thinking is on the construction of these forms. So here's a thin shell form. Obviously, again, once again, supposedly done without formwork. Um, I think it's really neat to look at the facility that this is being done in. This is like a college, a technical college or European research group. But we have these all kinds of automated, advanced computers driving robot arms on gantry systems. Really sophisticated, cutting-edge type of research and facility. So the idea here was they were to build a thin shell structure in an innovative way. And once again, you can see it being pulled apart here. So we have substructures, we have a cable net grid system, we have a fiber system, or excuse me, this might be a fabric barrier, then a fiber reinforcement, and then finally a concrete shell to it. And if we roll back here underneath the words, we can see a lot of this. Oh, it disappeared so quickly, I'm sorry. You see all of this still underlying structural systems to hold everything up in place. There we go, it labels it for us. I'm really amazed at these really fancy looking connector systems. To think that they're all buried in concrete seems such a waste of that beauty, of that complexity. So here they are laying up that mesh. It looks like this, just we can stop here. This looks like a Rhino building environment. So just as an idea of what software is being used, this is for sure Rhino. And then they are putting the coating systems on it. And I think the plastic sheet is to control the curing time of the concrete that gets applied to it. And it looks like they pull down that cable system then once they're done. So maybe those are reusable components. So this may be where the future of thin shell concrete systems goes. It's up to the future to find that out. So that pretty well covers just a brief, I guess, stimulation on the idea of concrete. What I really want to do now is think about where we will go with the idea of T-splines. So just to back up a little bit, one of my thoughts for linking T-splines with concrete was in the project that we're going to work on, where T-splines lend themselves to this monolithic or monochromatic surface. And I thought it would be a good way to look at these thin shell materials or concretes as a way of producing these. But it also is kind of a reach, so these don't necessarily have to be made out of, conceived and or made out of concrete. So a little bit on T-splines, and one of the reasons why I want you to experience T-splines is they offer a unique way of thinking about creating modeling forms. They come from, this is a link to Autodesk, and they come to us from an industry at an Autodesk level of product design, where they needed to create these really complex curved shapes, and they needed easy ways to define those. And also Grasshopper is really advanced, or excuse me, Rhino is very advanced in the concepts of T-splining. Just a brief idea about it. T-spline, kind of like a three-dimensional NURBS curve. We have a control point, and then the shape is generated from that. It really reduces the complexities of the shape, of the definition of the shape, and really empowers the modeler with the tools they need to create really fast and high quality surfaces. So this is a student. I'll just run through this who's using T-spline concepts to create a shape form of an existing building to show how it would be done. So you can go, it always starts in the wrong spot. I'm already in the middle of things there. But the idea here is she's using the image to then come up with these basic forms that are created in Rhino. So this is really quite a nice tutorial. And then working with those, extruding them up and starting to work with those in three-dimensional geometry. And kind of the beauty of the system is when we get to this idea of what you can do to manipulate these forms very quickly. And that squaring of it is just like a cruder preview before it goes to a higher resolution rendering of the form. So she's just showing how she can close up those forms. And then you can see where it pops back to a T-spline surface. And I'll need to pause that so that it's not running while I go back to our slideshow. And so Autodesk is also, like I said, trying to introduce these T-spline, but it's coming from their product development end. And for that reason, the implementations inside of Revit are rather crude. Both Dynamo and Revit are relatively crude at this point. Just a little visual description of the power of T-splining. So here we have this idea of pipes, and then we can define the way those pipes come together in order to create these nice smooth transitions, and we can create different value systems for them to really significantly alter their appearance. There are a couple of companies that are using those technologies in different ways, but they're still kind of related to me to our architectural endeavors. So here's a company that's really advanced nervous systems. If I click to their site, I need to go to the generative design area, and I need to find a custom place to create this here. Let's try the custom ring. So here we're popped into a modeling environment where we can actually make adjustments to these systems. And I'm not exactly sure how all of these happen, but let's say we'll change the shape to a sculpture, and we'll hit build it. And we can adjust the kind of structure that goes along with it in real time. And then I believe we can just touch these points and divide them up further. So we have a lot of ideas about the way we can control the twist, inside outside twist, the shape. So this, to me, a very fascinating look at what I think the basis is that same idea of T-splining to create these really very complex and visually interesting surfaces. And this is happening in real time inside of a browser, which makes it to me all the more remarkable. And then at the real stretch of where we're going with complex surface creations, I thought this was a good place to put this in. This is Neri Oxman at MIT. And they have created a robot and then mass-produced that robot as a manufacturing machine. It contains a ribbon fiber, and it can weave its own structure as it climbs up through it. The group is called the Mediated Matter Group. So this is the construction parts. You can see it in operation, the idea of how it weaves as it progresses up. And then probably when it's done doing a certain section, it works its way up the there we go, it works its way up the construction. And a little bit of tilting will allow it to direct its form in any direction. So these are obviously really far out advanced ideas about architectural and or artistic construction systems. So that's at the far out, and now maybe to bring it back down to earth, these are 3D printed shapes that are applied as a second facade to a building, and I think it's more in the realm of something that we could conceive of and include in our project. And this is obviously very similar to what you'll be doing if you do the T-Spline project. So that concludes our really brief discussion of concrete and T-splines.